Alcohols are some of the most versatile functional groups in organic chemistry, serving as essential building blocks in synthesis. Because the hydroxyl group itself is a poor leaving group, many of these reactions begin by activating or transforming the hydroxyl group. In this video, we'll take a closer look at their most important reactions. We'll start with substitution reactions that produce Alkyl halides and sulfonate esters, which are key strategies for hydroxyl activation. Then, we will explore elimination to form alkenes and the oxidation of alcohols into various carbonyl compounds. Section 1. Substitution reactions, converting alcohols to alkyl halides. For primary alcohols, the substitution predominantly follows an SN2 pathway. The process begins with activation. The lone pair on the alcohol oxygen attacks the acidic proton of HBr. This protonation converts the poor hydroxyl group into water, a much better leaving group. Once activated, the bromide ion, acting as a nucleophile, initiates a backside attack on the carbon bearing the leaving group. In a single concerted step, the new CBr bond forms as the CO bond simultaneously breaks. This results in inversion of configuration, yielding the primary alkyl bromide. For more substituted or resonance-stabilized alcohols, the mechanism shifts to an SN1 pathway. After the initial protonation to form a protonated alcohol intermediate, the reaction proceeds via heterolysis, where the water-leaving group departs on its own. This creates a planar carbocation intermediate. Because this bond-breaking step is the most energy-intensive, it serves as the rate-determining step. For allylic and benzylic systems, this intermediate is further stabilized by resonance. Finally, the halide nucleophile attacks the vacant p orbital from either side of the plane, typically resulting in racemization. To avoid harsh acidic conditions and possible carbocation rearrangements, specialized reagents, such as PBr₃ and SOCl₂, are commonly used. In the PBr₃ mechanism, the oxygen of the alcohol attacks the phosphorus atom, displacing a bromide ion to form a phosphorus ester intermediate. This converts the poor hydroxyl leaving group into an excellent leaving group. The displaced bromide ion then performs a backside attack on the carbon via an SN2 pathway, resulting in the alkyl bromide with inversion of configuration. Similarly, SOCl₂ reacts with the alcohol. In the first step, the oxygen of the alcohol attacks the sulfur atom, forming a tetrahedral intermediate as the pi electrons push up to the oxygen. This intermediate then collapses, reforming the SO double bond and displacing a chloride ion to form a chlorosulfite intermediate. For visual clarity, we've represented this addition-elimination process with a gray arrow from now on. The presence of a base like pyridine is especially important here because it determines the stereochemical outcome. When pyridine is present, it deprotonates the intermediate and promotes a standard SN2 attack by the chloride ion from the backside, leading to inversion of configuration. In contrast, SOCl₂ without a base follows the SNI mechanism. After forming the chlorosulfite intermediate, the carbon-oxygen bond breaks to create a tight ion pair. In this intimate state, the chloride ion performs an internal return from within the ion pair, attacking the carbon from the same side as the departing oxygen. This unique internal attack preserves the stereochemistry, resulting in retention of configuration. Section 2. Sulfonate ester formation, converting alcohols to Tosylates and Mesylates. Sulfonate esters, such as Tosylates and Mesylates, are powerful tools in organic synthesis. Here, we see the two most common reagents: methane sulfonyl chloride, abbreviated as MSCl, and para-toluene sulfonyl chloride, known as TSCl. Since the hydroxyl group of an alcohol is a poor leaving group, we often convert it into these sulfonate esters to make the molecule highly reactive toward nucleophiles. These groups are exceptionally useful because the resulting sulfonate and ions are highly stabilized through resonance, providing them with excellent leaving ability. Forming a sulfonate ester, such as a tosylate, is a key strategy to activate alcohols without breaking the CO bond. The mechanism starts with the alcohol oxygen attacking the sulfur atom of TSCl, leading to the displacement of a chloride ion. This forms a protonated intermediate. A base, typically pyridine, then performs deprotonation to neutralize the HCl byproduct and stabilize the final ester. Crucially, because the reaction only breaks the OH bond, the stereochemistry of the chiral center is perfectly preserved. This leaves the molecule primed for a subsequent SN2 or E2 reaction with its configuration intact. Section 3. Elimination reactions, dehydration to alkenes. Secondary and tertiary alcohols generally follow an E1 mechanism. Under acidic and heated conditions, the acid first protonates the hydroxyl group, converting it into water molecule, a good leaving group. Water then departs to generate a carbocation ion intermediate. Even in structures prone to rearrangement, a minor pathway may occur in which the product forms directly from the initial carbocation ion without structural change. However, as seen in this example, secondary carbocation ions more commonly undergo rearrangements, such as 1,2-hydride or methyl shifts, to form a more stable tertiary carbocation ion. Once the cation is stabilized, a weak base such as water removes a neighboring beta proton, and the electrons form the double bond. According to Zaitsev's rule, the more highly substituted and therefore more stable alkene is the major product. Finally, removal of a different beta proton can also occur, producing a less substituted alkene as a minor product. In contrast, primary alcohols cannot easily form unstable primary carbocation ions. Therefore, they proceed through a concerted E2 mechanism, which typically requires higher temperatures to overcome the activation energy barrier in a single step. After protonation, a weak base removes a beta proton, while the water-leaving group is simultaneously ejected. In this single, concerted step, the CH bond breaks and the new pi bond forms at the same time, establishing the double bond without ever forming a carbocation intermediate. For alcohols prone to unwanted rearrangements, or those sensitive to strong acids, phosphorus oxychloride, POCl₃, in pyridine, serves as a powerful alternative. This reaction proceeds via a concerted E2 mechanism, even for secondary and tertiary alcohols. The alcohol first reacts with POCl₃ to form a dichlorophosphate ester intermediate, transforming the hydroxyl group into an exceptionally good leaving group. Pyridine then acts as a base to remove a beta proton, leading to a concerted elimination. Because this method bypasses carbocation formation, the carbon skeleton remains intact, providing a clean route to the desired alkene without any structural shifts. Section 4. Oxidation reactions. Conversion to carbonyl compounds. Oxidation of alcohols increases the number of CO bonds while decreasing the number of CH bonds. Whether the reaction stops at an aldehyde or proceeds all the way to a carboxylic acid depends on the oxidizing agent and the reaction conditions. For full oxidation, strong chromium-based reagents under aqueous acidic conditions are typically employed. These include chromium trioxide, CrO3, in aqueous sulfuric acid, commonly known as the Jones reagent. Alternatively, chromic acid, H2CrO4, or dichromate salts such as sodium dichromate, Na2Cr2O7, and potassium dichromate, K2Cr2O7, in the presence of hydronium ions, are used to drive the reaction to the carboxylic acid stage. For controlled oxidation, where a primary alcohol must stop at the aldehyde stage, milder or anhydrous reagents are preferred. These include pyridinium chlorochromate, PCC, which prevents overoxidation by excluding water. More modern and selective non-chromium methods are also common, such as Des-Martin pyridinane, DMP, or the Swern oxidation, which employs dimethyl sulfoxide, DMSO. Understanding these tools allows us to precisely manipulate molecular structures, beginning with the electron transfer events of the chromate-mediated mechanism. The process begins when the lone pair on the alcohol oxygen attacks the electrophilic chromium center. As the new bond forms, the pi electrons of a CrO double bond shift onto the oxygen, weakening the double bond. To stabilize the intermediate, proton transfer from hydronium occurs to a chromium-bound oxygen, while surrounding water molecules facilitate the proton transfer steps. Next, further protonation by hydronium ions converts a chromium-bound oxygen into a protonated leaving group that can depart as water. Loss of water completes the formation of the chromate ester intermediate. This CrO-C linkage then undergoes an E2-like elimination. A water molecule acts as a base, abstracting the alpha proton. The electrons from the CH bond flow to form the new CO pi bond, while the chromium group departs, reducing the chromium center. Under these aqueous acidic conditions, the reaction does not stop here. The presence of water leads to the hydration of the carbonyl group. A water molecule performs a nucleophilic attack on the aldehyde to form a gemdiol, or aldehyde hydrate. This hydrate then undergoes a second oxidation through the same chromate ester mechanism, ultimately yielding a carboxylic acid as the final product. In contrast, when using PCC, the reaction is carried out under essentially anhydrous conditions. Instead of water molecules, the pyridinium ions and pyridine molecules present in the medium facilitate the proton transfers required to stabilize the intermediate. Once the chromate ester is formed, the final redox transformation occurs. In this anhydrous environment, a chloride ion, or a pyridine molecule, acts as the base to abstract the alpha proton. As the CH bond breaks, its electrons flow to form the aldehyde CO double bond, while the chromium center is reduced. Because the medium is essentially anhydrous, the resulting aldehyde cannot undergo hydration. Without the formation of a gemdiol, the oxidation process stops precisely at the aldehyde stage, allowing for the selective synthesis of aldehydes. Secondary alcohols are oxidized to ketones through a precise sequence of steps. Notably, this transformation works with various oxidizing agents, including Jones reagent and PCC, because the reaction naturally halts at the ketone stage. The process begins as the alcohol oxygen attacks the chromium center, forming a coordinated intermediate. Proton transfers then generate a suitable leaving group, and loss of water establishes the chromate ester linkage. Next, the mechanism proceeds through an E2-like elimination. A base, such as a solvent molecule or a counterion, abstracts the alpha hydrogen. The elimination is favored when the alpha hydrogen and the chromate group adopt an approximately anti-periplanar arrangement. As the proton is removed, the electrons flow to form a stable CO double bond, while the chromium center is reduced. While ketones can form hydrates, These species lack a hydrogen on the carbon, bearing the two hydroxyl groups, and are therefore not readily oxidized further under these conditions. As a result, the reaction stops predictably at the ketone stage. Tertiary alcohols are notably resistant to standard oxidation. While the oxygen atom can still attack the chromium reagent to form a chromate ester intermediate, the process stalls at the elimination step. This is because a tertiary alcohol has no alpha hydrogens. The central carbon is bonded only to other carbons. Without an alpha proton to remove, the base cannot trigger the elimination necessary to establish a CO-pi bond. Breaking a stable CC bond to force oxidation would require extreme conditions. So, under standard laboratory protocols, tertiary alcohols remain unreactive. In this video, we explored the core reactions of alcohols, from activation of the hydroxyl group to their conversion into halides, ethers, alkenes, and carbonyl compounds. Understanding these fundamental transformations is an important step toward mastering organic synthesis. In future sessions, we will dive into more advanced topics, such as Fischer esterification for creating esters, and the strategic protection of alcohols, using silyl ethers to shield them during multi-step synthesis. If this video was helpful, we'd really appreciate it if you could share it with others. See you in the next reaction.